Hello, this is SND College of Engineering and Research Center, Yeola. Lecture series for first year engineering. I, Dr. Chaudhary Vivek Sitaram from first year engineering department. Now, today we see the significance of wave function. As we know, wave function is the function of space and time. That is nothing but it is a function of x, y, z and coordinate time, that is t, and is generally a complex quantity having no direct physical significance. The probability of finding a particle at certain point can never be negative, as probability can have values between 0 and 1. The wave function psi is not an observable quantity. The probability of experimentally finding the body described by the wave function psi at point xyz at time t is proportional to its value mod square of psi there at time t. The larger the value of mod square psi means stronger probability of object's presence. The smaller the value of means lesser the probability of object present over there. As we know, wave function psi is a complex quantity. So it is equal to A plus IB. So its complex conjugate will be A minus IB. So psi star is equal to A minus IB. And the mod square of psi is equal to psi into psi star is equal to A square minus I square B square, which is equal to A square B square, which is always a positive quantity and real quantity is required. So, and which gives the probability of finding that particle over that space and at that point of time or at that time. So now there is a normalization. The wave function must be normalized, since the mod square of psi is the probability density of finding the object described by the psi. So what is this? It is the probability of density of finding the object over all the space. So it must be finite and having a single value. So because object has to be somewhere into the space, that is from minus infinity to minus infinity, and it should be equal to 1, that is nothing but the normalization. So, and if it is equal to 0, the particle doesn't exist. So obviously this integral cannot be infinity and still means anything. Non-normalized wave function cannot represent particle. A normalized wave function stays normalized forever. Now conditions for well-behaved wave function. So now as we know, psi is the wave function. And what is wave? That is from the matter wave. That is from the de Broglie hypothesis. Every moving particle having the mass m and velocity v is associated with a wave, and that wave is nothing but the matter waves, and psi is the wave function. So psi must be continuous and single valued, because probability can have one value at particular place and time and continuous. Now second condition is that momentum considerations require that partial derivative of that should be finite, continuous and single valued, and psi must be normalizable, which means psi must go to 0 as x tends to infinity, plus minus infinity, or y tends to plus minus infinity, or z tends to plus minus infinity, in order that probability of finding the object over all the space is finite constant. For normalizable wave function, the probability that the particle will be found between x1 to x2 is nothing but, that is probability that the particle will be found. P x1 to x2 is equal to integration from x1 to x2 mod square of psi dx, if the motion is restricted between these two directions. Now the expectations value. How to exact information from the wave function we come to know. The wave function psi, which is the function of space and time, that is psi is the function of x, y, z and t, contains all information about the particle permitted by uncertainty principle, that is Heisenberg's uncertainty principle. So suppose if a particle is confined in x direction, then expectation value is given by x, expectation of x of position of the particle described by the wave function psi, and can be calculated. And average position of the number of identical particles distributed along x-axis such that n1 particles are x1, n2 are at n2. So there is the summation and which is given over here. When dealing with single particle, the number of particles at xi is replaced by the probability that the particle is found in the interval dx at x, very small, and so that is probability of finding the particle is equal to mod of psi square into dx, where psi is the particle wave function, making these substitutions. So expectations values can be given as expectation of, that is psi, that is x over here capital psi, from minus infinity to plus infinity, x in mod square of psi dx. So physically the expectation is the average of measurement performed on the particles all in the state psi. It doesn't mean that if you measure position of one particle again and again, so x will be the average of the results. So from these expectations, the expectations value of the momentum cannot be calculated this way, because uncertainty principle doesn't allow that, because px is equal to mv, so m into dx by dt. So rate of change of displacement is nothing but the velocity. If x is specified, then dx will be 0, and then corresponding momentum p cannot be specified, and that is from the Heisenberg's uncertainty principle. There is the uncertainty in the measurement of position and momentum simultaneously should be greater than or equal to h cross or h upon 4 pi. The same problem occurs for the expectation values of the energy and the expectation values of momentum. Again, the kind of limitation is not observed in classical mechanics. So now there is an operator, another way to calculate expectations value. As we know, a free particle wave function is given by psi is equal to a e raised to minus I upon h cross into et minus px. So if we differentiate it with respect to x and t, it gives the delta psi by delta x is equal to I upon h cross p a e raised to minus I upon h cross et minus px, and which is equal to I upon h cross p psi. So similarly here, delta psi by delta t gives I h cross delta psi by delta t. So p psi and e psi, from this value, so we know the energy is nothing but the sum of kinetic energy and potential energy, and from that equation energy E is equal to p square upon twice m plus u. And from this equation we come to know, if we put the value of IH cross delta by delta t and IH cross delta by delta t, p psi and e psi in the given equation, so IH cross delta psi by delta t is equal to minus h cross square upon twice m delta 2 psi by delta x square plus u of psi. This is Schrodinger's equation in one dimensions. So similarly we can calculate the expectations value. Thank you very much.